Hello and welcome to our classwork video for today entitled 2.5 Powerful Tens. Before we get started, I want to talk about something called common logarithms. Those are when if you have a base of 10, that is usually kind of taken out and just assume that that's just log of x. That is because 10 is the most common base you see used in science and other fields. You might think of scientific notation as an example that's widely used that relates to that. For example, if we grab our calculator, we can see that we have, say, log of 10. That equals 1 because 10 to the power of 1 equals 10. And that will be used a lot in this classwork video. So to start off with, we are looking at some tables here in number 1A and B, and we were trying to fill in all the missing parts of this table. So we have some filled in already in part A, and we're looking for just two missing x values on the column on the left. So the fourth row is a little bit easier because it is basically asking us 10 to some power equals 100. Well, we know that answer is just 2. So that is easy to solve without any extra effort. Now, 50 is a little bit harder because there's no 10 to a power. It doesn't give you exactly 50. If 10 to the first power gives us 10 and 10 to the second power gives us 100, this x value is going to be somewhere in between 1 and 2. So this unknown x is going to end up being equal to, 10 to some power x is going to be, let's rewrite that. So we have 10 to some power is supposed to equal to 50. Well, if I think about what we know about logarithms now, I can rearrange that equation as log base 10 of 50 is equal to x. And that is the same thing as just log of 50. So we grab our calculator and use log button 50 to get an answer of about 1.7. So right in between 1 and 2 like we guessed. So our first table is pretty easy. Now in our second table, part B, we have a little bit more work to do. We have 3 missing x values that we're looking for. So now some of them are going to be easier to find than others in this one. So let's see if we can figure out what we're doing. So for our first one, we have our x equal to 0.3. So that'd be 0.3 is equal to 3 times 10 to the power of x. Now, if I'm going to solve this, well, this 3 in front I could divide by. So if I divided both sides by 3, that means I would have 0.1 is equal to 10 to the power of x. So 0.1 is actually the same thing as 1 over 10 equals 10 to the x. Well, I know that 10 to the negative 1 is the same thing as 1/10. So that's an example where we don't have to use our calculator for that quite yet. If we look lower down at some of the other rows here, well, we have 94.87, 1503.56. Those are definitely going to be ones we're going to have to use our calculator for since those are decimals. So our first one we have is 94.87 equal to 3 times 10 to the x. So now if I'm going to do that, well, the first thing I would do is divide by 3. So I can do 94.87 divided by 3, and I get 31.623 and equal to 10 to the power of x. So now once I'm here, well, since this is just 10 to the x, I can rewrite that as a logarithm. So I have log base 10 of my answer there of 31.623, and that will equal x. So I just put that into my calculator, and we can see that happen maybe. So that would be log of 31.623, and that would equal 1.5. Now our last one is this missing x value right there. So now we are just going to have 1503 3.56 equal to 3 times 10 to the x. So now if I divide both sides by 3, just like last time, I am going to have 1,500. So we have 1,503.56 divided by 3 is 501.19 is equal to 10 to the x. And then we just rearrange that as a logarithm. And that would mean log base 10 of 501.19 equals x. So we just do log button of 501.19, and we get 2.7. So these 1.5 numbers, 2.7 numbers, and then the 1.7 in the first table, those are great examples where we have to use a logarithm in order to get our answer. We can't just find it using exponent rules like we did with, say, this 2 right here, or with the -1 in our second table. So if we think about our next question, what equations could be written in terms of x only for each of the rows that are missing the x in the 2 tables above? So generally speaking, if you know your y value and you're trying to find your x value, well, if you invert everything or find the inverse of your function, that would have your x now be your output, your original y then becoming your input. So if we wanted to do that, so we can do our first one, we'll do that in blue again. So now if we have in blue, we have 10 to the x is equal to y. So if I want to have it in x is what I'm going to be equal to, so I can solve for x. Well, my 10 is my base, so I could rearrange that to log base 10 of my y value is now going to be equal to my x value. And that would be able to work for all the second column of that first table. So now for the other one is a little bit trickier, but only by kind of one extra step. We have 3 times 10 to the x equal to y as our equation for that table. So if I divide by 3 first, I then have y over 3 on the right side. And then I now can convert this into a logarithm. So that logarithm that I would be converting into would then have be log base 10 of y divided by 3 is equal to x. I undid each of those parts. And these would kind of be the inverse functions if we then just switched x and y. But we don't want to go all the way that way. We're just trying to solve these equations. Okay, so now moving into the next tables of this process. So now we have our table D. So we notice that we have -2, -1, 1, and then 1.6 and 2. So our y's are going up by 1, and then our x's are going to be changing. So for instance, for these first missing x is going to be an easy one to find, because we have basically -1 is going to be equal to log of x. So it would just end up being 10 to the -1 is equal to x. Well, that's easy. 10 to the -1 is just 0.1. We had that one earlier. And then the second one, also pretty straightforward. We now just have 1.6 is equal to log of x. And so now that 1.6 is going to be 10 to the 1.6 equal to x, and 10 to the 1.6 power in our calculator is 39.81. So we're able to fill in that. And so while we're working on this one, our next question is going to ask us how to get the equation for x. If we take our equation, we have basically just y equals the log of x. Well, if we rearrange that, we have a 10 that we can write in at the bottom there. And so now it would just be 10 to the power of our y value is equal to our x value. And we're just kind of rewriting it and then reversing it using our logarithms. Lastly, we have a sort of different one. So you remember from last time from Thursday, we talked about transformations. This would be a parent function of the one to the left. But this one has been shifted to the left three spaces. So we have three y's to find at -2, 0.3, and 3. So we have a couple of extra steps, but not too bad for this one. So if I have -2, so that means that -2 is going to be equal to the log of x plus 3. So I would do 10 to the -2 equals x plus 3. And then I would just be doing 10 to the -2 and then minusing 3 from that to get my x value. So if we grab our calculator, we can do 10 to the -2 minus 3 equals -2.99. So same thing for the next two rows. We would have 0.3 equal to the log of x plus 3. And then we have 10 to the power of 0.3 equal to x plus 3 when we rearrange it. And then we just be subtracting 3 from both sides to get 10 to the 0.3 minus 3 equal to x. 10 to the 0.3 power minus 3 equals -1.005, which you probably could round to -1.01. Doesn't make a really big difference here. And then lastly, for this table, we have 3 is equal to the log of x plus 3. It's going to be a pretty big number now because we have 10 to the power of 3, which is 1,000, and then x plus 3. So if we have 1,000 minus 3, well, that's 997 is equal to x, which is our last number. For this table E, if we're trying to get an equation, just solve for x. Well, we would write our equation first. Y equals the log of x plus 3. So we would do 10, which is like remember, that's what's missing. If there's not a base, it's always 10. So we would have 10 to the power of our y value equals to x plus 3. Well, that would mean that our equation, as you may kind of have surmised already, would be 10 to the power of our y value minus 3 gives us our x value. And so we have done a lot of practice here with reversing our equations to get the x values that we need. We solve for x if we knew the y value in all of these. Moving to the back, we already did f. Well, we just finished doing that. So we're going to move to 2 and 3. So number 2, what strategy did you use to find the solution to equations generated by the tables that contain exponential functions? So those ones that contain exponential functions was table A. So we used a logarithm function to undo that and solve for x. And then in table D, no, we only have one. Well, I guess the table B would be the other one. In table B, we have a logarithm function that we use to undo that one as well. For that one was log base 10 of y over 3. Undid that and was able to give us an equation to use to solve for x. And then basically the opposite is true. When it contained a logarithmic function, we had to convert it to an exponential function in order to solve for an answer. So when it contains exponential functions, we used logarithm functions to undo and solve. And then we did the opposite with ones that contain logarithm functions. We used exponential functions to undo and solve those. And we'll see different situations in the rest of this chapter where we're going to start out with an equation that might be a logarithm equation, or it might be an exponential equation. And we're going to be looking for these strategies and using the opposite to undo it, just like if you use addition to undo a subtraction equation. Same idea that's happening here. Moving to part 2 of our classwork here, we're looking at some graph puzzles. So remember when we were looking at this equation here, this is y equals 10 to the negative x. So if I wanted to just use my graph to solve this, so remember that I am looking for the x value because this graph is 10 to the negative x. So that the x value you're looking for would hit this y value, the 40 right here. So when y is 40, that is about right here. And that is A. So that at 40, that looks like it's about 1.8 or so. A little hard to tell on the graph that we have in front of us, but we can make that assumption that we have that approximately right. So maybe negative 1.8, negative 1.6, kind of somewhere around that region would be close enough, I think. So we'll say negative maybe negative 1.7 for x. So now our y here is 10. Now 10 would be about here. Move this different color in purple. So for b, that's 10 right there. So it looks like we're at about negative 1 for our x value that we're looking for point b. So we have negative 1 as an answer. And then our third y value that we're looking for is 0.1. So 0.1, well, that's going to be very, very small for our answer there. And we may want to use a little bit of a calculator help here. So remember, if we are looking at this, if we reverse that into a logarithm function, we would be doing log base 10 of 0.1. And that would be equal to negative x as our logarithm function there. And if I wanted to try to solve that, well, if I figure out what log of 0.1 would be equal to, well, that equals to negative 1. And so that means that it would be equal to 1, which would be right here for point C. A little hard to tell on our graph. If you graphed this equation right here in Desmos or on your graphing calculator, you'd be able to be a little bit more accurate. So that's our first graphing puzzle done right there. You kind of see how it's kind of reducing with our y value from 40 down to 10 down to 0.1. Moving onwards, we now have a new graphing puzzle here. For number A, our letter A, we have our function. So basically that's the vertical shift down 2, and we have our original function up here at the top. And we're looking for the y values. So when y is negative 2, that's right here. That is going to be A. So our x value is 1 when y is negative 2. Our second y value is 0. And so our y of 0 would be up here. But we can tell that, well, we're not actually going to reach that based on just looking at the graph here. So we have to think about this a little differently than the last one we did. And we basically would need to figure out, well, what is going to be that value? So if I think about this in terms of algebraically, well, that would mean that I would be adding, if I added 2 to both sides, for instance, that would be log base 10 of x is equal to 2. So I would just be doing 10 to the second power equals x. Well, that's just 100. So 100 is obviously off our graph since our last number is 13. For part C, well, we're not, if we add 4 or add 2 to both sides, well, that would mean we have negative 2 is equal to the log of x. Well, 10 to the negative 2 is going to be equal to 1 over 100. So 1 over 100 would be really, really close to our y-axis when we have negative 4 all the way down here. So it would be kind of right there for our C value, being 1 over 100. And so part D, continuing with this, negative 1.3. Negative 1.3 would be kind of right, let's be right there. So if I follow that across, it looks like I'm at about 6. So I can just go with 6 as my answer. And then if my last one, I'm supposed to equal to 1. But if I look at my graph here, at 1, it may be a very, very big number before we get to 1. So let's see if we can solve that one algebraically real quick. And so that would be, if I added 2 to both sides, that means that I have 1, or 3 actually, is equal to the log of x. And that would become 10 to the third power is equal to x, which is 1,000. Obviously not something we would see on our graph. Number 6 axes are these solutions you found exact or approximate. It kind of depends on which one we were looking at. D, when we got 6, that was kind of an approximate. We were looking at about 6. Same with A, when we got 1 as an answer, that was approximate as well. And depending on the problem we're doing, we could use graphic technology like our calculators or Desmos to do that. Or we could do some solving like we did right here. And that equation solving is something we're going to be exploring with 6 different examples in the next part of this lesson. We're going to be solving these 6 equations in the second part of this lesson here. In number 7, we have 10 to the x equals 10,000. Sometimes you'll have equations where you will just know the answer. We mentioned before 10 to the third power equals 1,000. Well, that would mean that 10 to the fourth power has to equal 10,000. So we can just kind of say right away that the answer is 4. And that's very possible in lots of different examples. You might just know the exponent that's going to be giving you the answer. 8 is a little bit harder, but not by much. We just basically have to rearrange this exponential equation into logarithm form. So the logarithm form of that would be the log base 10 of 125. Or if we go to our calculator, log button of 125 would be our answer. And so log of 125 equals 2.097, which you could round to 2.1 if you so chose. And the third problem here on the front page that we'll do, 10 to the x plus 2 equals 347. So just like before, we want to rearrange it into logarithm form. So what that would look like would be the log base 10 of 347 equals x plus 2. Now, I could put log base 10 or log of 347 in my calculator, but I'm going to do that second. And first, I'm going to subtract 2 from both sides. So it would be log base 10 of 347 minus 2 is equal to x. And then I would just put all of that in my calculator all in one go. So it would be log of 347 minus 2 equals our answer of 0.54. And that finishes number 9. We will flip to the back for number 10, 11, and 12. All right, 10 to start off with. If I have 5 times this exponent part equal to 0.25. So if I divide both sides by 5, I would have 10 to the power of x plus 2 is equal to 0.05. Now I can rearrange it into a logarithm. So that would be the log of 0.05 equal to x plus 2. And I'd be just subtracting 2 like in number 9 that we just did from both sides. So I'd be entering in log of 0.05 minus 2 is equal to x. And that, if we put right into our calculator, ends up equaling negative 3.3 for x. Number 11, we have, well, let's give you guys a second to copy that down if you need to. So our answer, negative 3.3 for that one. Number 11, we have 10 to the negative x minus 1 equals 1 over 36. As before, our first step is turning it into logarithm form. So I have the log of base 10 of 1/36 equal to negative x minus 1. And from there, I'm going to add 1 first. Do this one step at a time. And that's equal to negative x. And then lastly, I just have to divide by negative 1. So if I do that, each thing on the left side would just become the opposite. So I would have the negative log of 1/36 minus 1 equal to x. And if I put that as is into my calculator, I would get that the answer is equal to 0.556. Last problem, and the last thing we'll do in this video, is number 12. And that, our first step is going to be dividing by negative 1. That's what that negative in the front means. It's actually kind of like a negative 1 right there. So that means I have 10 to the x plus 2 is equal to negative 16. So now I can rearrange it into a logarithm. So I have the log of base 10 of negative 16 is equal to x plus 2. Now I can put the 2 to the left side by subtracting 2 from both sides. And that would give me the log base 10 of negative 16 minus 2 equal to x. And if I put all of that into my calculator, log of negative 16 minus 2, it gives us a non-real answer. So if I am thinking about this, just keep in mind that when you have log base 10 of x, for instance, that is going to be kind of starting at the x-axis and having a vertical asymptote at the x-axis. So generally speaking, if you were doing the log of a negative number like this number right here, well, that's going to be a non-real answer. Because you think about like 10 to a power is never going to get smaller than 0, because either going to be 10 times 10 times 10 get something, or 10 divided by 10 divided by 10, it's never going to get to 0 or lower. So sometimes you might have a case where there is no real answer, or you could say that there is no solution. And that concludes our video on solving exponential and logarithmic equations using base 10, using our calculators to help us out with that. In our next lesson, we will be going into some applications of logarithms and looking at some real-world scenarios as well. Thank you for watching.